there are two pendulums connected with a elastic cord. So initially P force is applied in upper direction on the pendulum balls and mg downwards. Then these balls are pulled apart like this. So let's consider this angle theta, and this force will be mg. This length is L, so this length will be L sine theta. So similarly, this length will be L sine theta. So because this is an elastic cord and initially this cord was unstretched, so this was applying no force on these balls, but now this cord is stretched, so this cord will apply a horizontal force on this ball. There will be a horizontal force in this direction, and on this ball there will be a horizontal force in this direction. Now let's take the torque about this point on the roof. So torque of mg will be mg uh, into this distance, which is L sine theta, plus torque of the force applied by this elastic cord, which is k into extension, which is 2L sine theta, into this length. So this length is L cos theta. So torque I can write equal to I alpha, fine, where I is moment of inertia. So moment of inertia for this ball will be ml square. Now mg L sine theta I can approximately write as theta because of small angle, plus 2k L theta into L cos theta I can write as 1 because theta is small, so cos theta will be equal to 1, equal to ml square d square theta by dt square. uh, Theta, if I take common, inside the bracket will be mgl plus 2k L square equal to ml square d square theta by dt square. Now we can see alpha directly proportional to theta. So this type of equation we already know, and we can easily write its time period. So t equal to 2 pi I by k, where I is this and k is this term, this whole term. T equal to 2 pi into mgl plus 2kl square by ml square. But if you think this is correct answer, you are wrong. This is not correct answer. The reason being that uh, when this string moves apart, then this cord will be elastic cord will be stretched, so it will be applying a horizontal force. But on the right hand side of equilibrium position, let's see, this was on initial position of our pendulums. Now when we pull apart this cord, they will get to these positions. Now in these positions the cord is stretched apart, so it applies a horizontal force. But on the second part, on the second half of the cycle, when these pendulum balls move to the move inwards like this. Now the cord is this cord is slacked. Due to slacking, this cord won't be applying any force in horizontal direction. This cord will only apply force when it's stretched. Unlike a spring applies a force when it's in compression and also when the spring is stretched. In both cases, the spring applies the force. But this elastic cord will get slacked in the second half of cycle. So this won't be applying any force. So for this half of the cycle, this half of the cycle, the time period will be half of this time period we found. So t half equal to pi g by l plus 2k by m. Then for the second half, how can I find the time period? For the second half, it is very easy. So this angle is theta. There's a tension T, force mg. So torque about this point equal to mg into L sine theta, which is equal to ml square into alpha. And this is the normal pendulum time period which we already know. So time period for this second half will be pi into g by L. So I will add this time period and this time period to get the total time period, which is equal to pi g by L plus 2k by m under root plus under root g by L. So this is our answer.